Hello everyone, my name is Max and I'm glad to present our work Anatomical Mesh-based Virtual Fixtures for Surgical Robots. This is a joint work between Johns Hopkins University and SICKIS Toronto. Virtual Fixture, which is a virtually implemented fixture to constrain or guide motion in software. This can further increase the efficiency and safety by providing the user appropriate assistance. In surgery, virtual fixture can be used to prevent the surgeon to damage critical anatomy. However, it is very challenging to automatically generate virtual fixture for very complex anatomies. Existing research mostly obtain an approximation of the anatomy using parametric form, for example, using an ellipsoid or sparse level set functions. To generate these virtual fixture, it is usually labor intensive, and the result is not very accurate. On the other hand, polygon mesh structures, which contain triangles, vertex, and face normals, can accurately represent the anatomical shape. It is widely used in medical imaging to visualize 3D shapes. Prior work proposed to treat all triangles as plane constraints to force the tool to be on the positive side, such that a protection layer is built around the anatomy. However, this is ill-posed and only works with concave objects. To demonstrate the idea, we use 2D geometries, where black lines indicate the triangles and the black arrows indicate the face normal, and the blue region is the anatomy. For a concave object, if all triangles are used as plane constraint, the red hatched region will be the forbidden region, and the algorithm can produce the desired constraint. However, for a convex object, the red hatched out region will remove many theoretically feasible regions as well, leaving only a small space for the robot to move. This is undesirable. Therefore, in this work, we propose another anatomical mesh-based virtual fixture, and we generate the virtual fixture for a complex anatomy automatically, and we do not make any assumption of the shape of the anatomy. We implement an efficient and dynamic formulation such that the algorithm can run in real time in kHz range. The proposed mesh-based constraint formulation is based on closest point and the local geometry. First, we store the mesh as a PD tree. A PD tree stores the triangles in a node and builds a bounding box around each node. The nodes are split along the most distributive direction, and the process is repeated to further divide the mesh. This allows for very fast geometric search. We define a motion sphere whose radius is defined by the maximum motion capable of the robot within one control iteration. Therefore, we can reject triangles that are far away than this radius, since the robot will not reach those triangles within this control iteration. Then, we determine the closest points of a point on a triangle of interest, and there are two possible cases. One is when the projected point is within the triangle, and the CP is the same location. The other possibility is the projected point is outside of the triangle, and the CP is on the closest edge. Next, we determine the local geometry by a simple dot product as shown in the equation here, where n is the normal and v is the non-shared edge of adjacent triangle. To illustrate this, these two arrows here are the vectors used in the dot product. As shown, when the dot product is positive, it's a concave object, and when the dot product is negative, it's a convex object. Thus, we have our mesh-based constraint formulation based conditioned on both closest point and also local geometry. To illustrate how this algorithm works, we'll use 2D illustrations and enumerate different cases. In the case of a convex object, the possible regions can be divided into 3 different sections, and the rest will be same due to symmetry. Given a robot tool position shown as a blue sphere here, if it is in region A and B, only plane 2 will be activated. Once it moves into region C, however, the activated plane will be defined by the vector pointing from closest point to tool position, thus approximating the sharp edge of a convex object. In the case of a concave object, there are 5 possible regions, and the rest will be same due to symmetry. If the tool position is in region A and B, both plane 1 and 2 will be activated. If the tool position is in region C and D, only plane 1 will be activated. Plane 2 we will need additional information of the neighboring triangles. If it is provided, it will be one of the previous cases we have enumerated. Similarly, if the tool position is in region E, we'll need the information of adjacency of both plane 1 and 2 in order to provide the constraint. We first evaluate our algorithm in simulation, where we have tested different objects as shown here. For these simple geometries, if the tool position is outside of the objects, we have a convex surface as illustrated here. Additionally, we show the tool position without virtual fixture, in other words, the commanded position as a red sphere, and the tool position with virtual fixture, in other words, the virtual fixture constrained motion, as blue sphere. As shown, the blue sphere can be successfully stopped at the exterior of the object, even if the red sphere enters the object. On the other hand, when the tool is inside the objects, is facing a locally concave surface as shown here. When the commanded position exits the objects, the blue sphere can successfully be stopped at the interior of the objects, thus demonstrating the effectiveness of our virtual fixture. For real-world objects, they usually contain both locally concave and convex surface as shown here. However, our algorithm is agnostic to local surface geometry and can successfully stop the tool from entering the objects. We also conducted runtime analysis to evaluate our algorithm. Our setup is shown here. As shown in the diagram, when the number of triangles increase, the speed of our algorithm drops gradually. When the number of triangles is in the order of hundreds of thousands, however, the frequency can reach kilohertz, which is desirable for a lot of robotics application. We conduct a real experiment to be applied for cranial synostosis. It occurs when one or more cranial structures prematurely fuse. The fused cranial structures do not allow for proper expansion of the skull as the child grows, and these cranial structures must be reopened by surgical intervention. This operation usually requires delicate tool movement and avoid incision-related complications, such as damaged dura. The system setup is shown here, where we use the Da Vinci research kit and a piezoelectrical cutter designed specifically for craniofacial surgery. We use a 3D printed skull phantom to represent the pediatric skull. We set up the virtual fixture such that the skull exterior surface is protected, and the 2 virtual walls are used to facilitate the path following. The first experiment is skull tracing, where the user is asked to trace the exterior of a skull along a already cut path, which is a straight line. So we want to evaluate the improvement of depth perception due to virtual fixture. Shown on the right is a cross-section of a pediatric skull. When there is no virtual fixture, the path is shown as the blue line here. we see a lot of adjustment based on stereo vision. On the other hand, when the virtual fixture is provided, shown as the green line here, even if the proxy path, in other words the commanded position shown as red, already penetrates the skull, the virtual fixture can stop the tool from entering the dura. Therefore, the green line follows the exterior of the skull best. The second experiment is skull cutting, where the user is asked to cut along the planned path. Here's the short demo of the actual cutting. We want to evaluate the improvement of the reduced penetration depth and also path deviation. Shown on the right are the cutting paths of the skulls cut by teleoperation and virtual fixture assisted teleoperation. The cut path is a straight line of 30 mm. We measure the deviation of the cut path every 1 mm interval as shown as the black short lines. Qualitatively, we see that the teleoperation has a much larger deviation from the planned path compared to virtual fixture assisted teleoperation. Before cutting, the interior of the skull is overlaid by a layer of wax. The penetration depth is measured as the offset between the exterior of the skull and the wax. We use a XYZ linear stage with a load cell mounted on it. A small tubing is installed on the load cell to detect contact. Therefore, we are able to measure distance. Of the two skulls cut by teleoperation and the two skulls cut by virtual fixture assisted teleoperation, we see that the cut path deviation has dropped from on average 0.63 mm to 0.37 mm with a much smaller standard deviation. As for the penetration depth, the absolute penetration depth has decreased from 0.83 mm for teleoperation to 0.39 mm for virtual fixture assisted teleoperation, also with a smaller standard deviation. Therefore, we conclude that the virtual fixture assisted teleoperation is more advantageous than teleoperation. The current limitation of our work is that it is position only, which means the rotation of the tool is not constrained, and we only did a proof of concept experiment. In the future work, we would like to extend this to a 6th degree of freedom, such that the rotation of the tool is also constrained. We would like to also conduct a larger scale of user study. I would like to acknowledge our funding source, in part by a research contract from Galen Robotics, Johns Hopkins University internal funds, and in part by Division of Plastic Surgery and Neurosurgery at Hospital for Sick Children. The open source implementation can be found at the link provided here, and if you have any questions, you can reach me via email at my email address. Thank you very much for listening to our presentation.